Welcome to Robominions.in AI interview preparation app. In this video, we will be looking into time and space complexity. So the topics will be covered is asymptotic notation, space complexity, big O complexity chart, and data structure algorithm complexity table. So let's look into asymptotic notations. There are three types of asymptotic notations: big O notation, theta notation, and omega notation. Big O notation, it is an upper bound of an algorithm. It provides the worst case time complexity of an algorithm, which is useful for the analysis. For example, the worst case time complexity of a bubble sort is order of n square. So this is how it is represented. Then we have theta notation. Theta notation provides exact bound. It's tightly bound, bounding both upper and lower side of the algorithm. Hence, it defines exact asymptotic behavior. Theta notation of an expression drops lower order terms and also ignores constants. For example, we have the time complexity as 50 into n raised to 4 plus 55 into n raised to 3 plus 500 into n plus 200. So theta notation of this would be theta of n raised to 4. 50, 55, 500 and 200 are ignored, and the lower bound elements like n cube and n are ignored, so only the n raised to 4 is considered. Then we have omega notation. It covers the lower bound of an algorithm, the best case time complexity of an algorithm, not much useful for the analysis of the algorithm. So example, omega of n best case lower bound time complexity of the bubble sort. So the omega of n is the best case lower bound time complexity of bubble sort. Then we have space complexity. So before that, we have something called auxiliary space. It is a temporary or extra space used by an algorithm. Space complexity is different from auxiliary space. Space complexity, so it's a total amount of memory space used by an algorithm. Space complexity is determined by calculating the total space consumed in an algorithm. So consider there is an array of integers of size n. Okay. So each integer will take 4 bytes. So array of size n will be taking n into 4 bytes. Okay. And then you have two integers in the program using 4 bytes each. So that will be another 8 bytes. So then space complexity of the entire algorithm would be n into 4 plus 8 total bytes. Okay. And the order of the complexity, space complexity would be order of n. So that is space complexity. Now let's look into big O complexity chart. So this is a complexity chart. So here is the number of operations and the number of elements. So the red ones, that is order of n factorial, order of 2 raised to n, order of n square, all these are very bad time complexity. Then we have orange, order of n log n, that is bad, and yellow, order of n is fair. Then order of square root of n is good, order of log n is good, order of 1 is very good. So that is the complexity chart. So then we have the order of here is the order, so the same thing. So 1 is very good, log n better than little bad than 1, square root of n little bad than log n, n bad than square root of n, n log n bad than n square bad than n log n cube bad than n square, and so on, and the worst is in this is n factorial. So now let's look at a code example for each of these complexities. Okay, so looking into order of 1. So in this program, so we are creating an array with the elements 1, 2, 3. Then we are printing a of 1. So that will be 2. Then the number of operations is just one operation. So it's order of 1. So end of the program. Now let's look into log n. So we are going to function 1, then going to j equal to 0. For I equal to 1, I less than n. So n is 8. So let's look at, so j plus plus, j is 1. So operation 1. So j has been printed. Now let's see. Operation 2. So function 1, you can see it has printed for log n times, that is log log of 8 to the base 2 would have been 3, right? So 3 operations have been printed. So the complexity of this function, time complexity, is order of log n. Now let's look at the function 2. So I equal to n, I greater than 1, I equal to I by 2. So j is incremented. So function 2, operation 1, operation 2, operation 3. And I greater than 1 is false now. So it's coming out of the for loop. So these are the so each function printed for log n times. So the time complexity is order of log n. So now let's look into the square root of n. So we are using the math.h and executing these operations for just square root of n times. So square root of 9 would be 3. So this operation would be executed for 3 times, as you can see, and then it comes out of the loop, and the time complexity is order of square root of n. So order of n. So this is example of a linear search code which executes for order of n times, that is the time complexity. So this is the number of elements is 8 and the search element is 99, so which is the last. So it has to go through all, linear search has to search for each element, and at the end it will find the key element and then that returns. Linear search. So for I equal to 0, 0 less than 8, I plus plus. So operation 1, operation 2, 3, 4, 5, 6, 7 and 8. So at this time it has reached the 99. So it will be the if statement, array of 8 is equal to search element 99 is true, so it returns the 8. So the element is present at index 7, so that's the 8th operation. So sorry, so it should have been array of 7 equal to search element 99, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, so 8th element, but the index is 7, so the index has been present. So the total operation is 8. So this is order of, the time complexity is order of n. Now let's look into order of n log n. So going to the function 1 with n equal to 4. So the operation 1, 2, 4, 2, 2, 3, 4, 3, 2, 4, 4, 4, 2. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. So total 8 operations. So n equal to 4, right? So 4 into log of 4 to the base 2, that is 4 into 2 is 8. So 8 operations are getting executed. So the time complexity is order of n log n. You can see this part of the function is executing 8 operations total. So that's the example of if the value of n equal to 4, so there is 8 operations with n log n time complexity. Let's look into order of n square time complexity code example. So we are going to n equal to 3, we are going to function 1. So I equal to 0, j equal to 0. So operation 0, 0. J has incremented, operation 0, 1, 0, 2. I is incremented 1 now. So 1, 0, 1, 1, 1, 2. Now j, now I is incremented to 2. So 2, 0. Then j is 1 now. So 2, 1, j is 2, so 2 comma 2. So then it's out of the for loop, then yeah, out of the function. So total number of operations is n square, that is 3 square is 9. So the time complexity of this is order of n square. Now let's see the example of order of 2 raised to n. So the code has to execute for 2 raised to 3, that is 8 times. So the operation will be starting from 1, so it will happen till operation 8. End of the for loop, comes out of the function. The time complexity is order of 2 raised to n. Now let's look at order of n factorial. N equal to 3, so n factorial function, n underscore factorial equal to 1, count is 1. So first the n factorial is getting generated, so it would be 1 into 2 into 3, that is 6. So the n factorial will be 6. So the number of operations will be 6 for this. Yeah, so you need to understand that n factorial, the number of operations for small number, even though it's the number of operations are small, but as the number grows, right? So 5 factorial is 120, but 5 square is just 25. You can see the difference, right? So when the number of when n value increases, the time complexity will be high, so the number of operations will be high. So yeah, so that is the big O complexity chart. So we saw how each individual complexity code examples. So now let's look at the data structure algorithm complexity table. So we have physical data structure complexity chart. So we have array. Array access is worst case is order of 1. Search is order of n, insertion is order of n, and deletion is order of n. Space complexity is order of n. Then we have singly linked list, then we have doubly linked list, then skip list. Please pause the video if you want to, and then you can study this and try to remember the complexity. And then we have logical data structures. So stack, queue, hash table, binary search, Cartesian tree, B tree, red black tree, splay tree, AVL tree, and KD tree. So this is the average and worst time complexity, and here is the space complexity. Then we have sorting algorithms. This is the best, average, and worst complexities. Quick sort, merge sort, tim sort, heap sort, bubble sort, insertion sort, selection sort, and this is the space complexity. Tree sort, shell sort, bucket sort, radix sort, counting sort, and cube sort. So this is the space complexity. So that's it for this video. So see you in the next video. And before winding up, just a quick reminder, I'm using the app Robominions.in AI interview preparation app. So this app is available in the website Robominions.in. Please go to this website and click on download. You'll have download for Windows OS. You can then click on that and download anyway, and you can start using the application. And you have in the app, you will have how to use the app option here. Please click on that, and you will get a video of how to use this app. Yeah, thank you. Have a good one. Signing up, Dhananjai Sharma,
founder of Robominions.in. Don't forget to subscribe to the YouTube channel, share with your friends and family. Visit Robominions.in website, crack your toughest coding questions and tech interviews by downloading latest version of the app, and make your coding easy. Thank you for watching this video. Bye.